Hello, welcome back. This is a super quick episode. I'm just looking at some smelting. Excuse me, got a frog in my throat. So a while back on one of JD's series, he had a smelting column which had productivity beacons, and there were some comments about how perhaps it could be improved. He then went away and improved the column greatly, and in some other series improved on that again. At the time I had a mock-up of it and a mock-up of some alternatives in creative mode, and I dusted them off today after a bit of a discussion with JD, and started trying to incorporate things that we've all learned since then. Okay, so let's turn on this. So this is a really simple, stupid smelting column. It is designed to eat one full column of ore coming in. And then with productivity mods, because we're eating one full column, we are producing slightly more than one full column of output. So you can see here, we're producing nearly a full column of blue, and most of an extra belt of yellow. There are some gaps in here, and that's because although there's clearly enough plates going through to fill up a blue belt entirely, we're not doing lane balancing anywhere. So there's when one side or the other is oversubscribed, there's no way to fix that. So we could actually fix this right now. Put in a poor man's lane balancer there. Okay. So now you can see this is full. We could do the same on the other side just for completeness sake. There we are. Okay, so we're producing one entire lane of copper plates plus most of a yellow lane of copper plates. And to do this, we need 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 of these smelters, which is fine. 15 furnaces is fine. This is an 8-8 type of build. Everything's quite spread out because we're grabbing the ore from the middle, putting it out to both sides. We're putting it out to both left and to right because we're outputting more than one full belt. Here, the first half of the stack goes to the outside of the belt, then in the middle we flip it over to be the inside of the belt, then we start filling the outside of the belt. All fairly standard stuff. Okay, so what can we do? Well, this is essentially the same build, except now instead of trying to consume a full belt of copper in, we are trying to fill one blue belt going out, so it's going to be shorter. Basically. So this was 15. This is 1, 2, 3, 4, 5, 6, then flip 7, 8, 9, 10, 11, 12, and then there's a final machine. Is this the 12th? Let's double check. 1, 2, 3, 4, 5. Yeah, so this is 12. And this nearly saturates the belt. You can see there's some gaps. Actually, to saturate it, you need a 13th machine. Let's put it here, which has an output to there, and then has a second output like that. And let's give it prob mods to make it happy. Okay, so that's your 13th machine, and this is slightly overproducing for the belt. So I think this produces roughly 41 plates, and the belt can carry 40. So these are your extra plates to fully compress the belt. So with a combination of this putting on the far side and this side loading onto the inside, now that side loading works, and now that inserters fill gaps, that's all fine. Okay, so that's cool. So that's 13 down from 15. We've got one single fully compressed line of blue rather than one and a bit. Okay, so that's good. What can we do? Well, this has a lot of empty space. And if you pick up one of these beacons, one fits there, and one fits there, except for there being a belt in the way. Well, that starts to make us think perhaps we could stick another couple of beacons in, and that would be 1, 2, 3, 4 extra beacons around one smelter. So that takes you from an 8 beacon build to a 12 beacon build. You'd hope that a 12 beacon build would decrease the number of machines you need. So if you went from an 8 to a 12 beacon and you started off with 12 machines, you go down to needing 8 machines. Okay, so let's see if that actually works. So this is essentially that. We've got the same outputting to the left, pulling off the middle. And I've put in the extra beacons. So each of these now is running at a crafting speed of 13.4 plus 570%, right, as opposed to these, which are 9.4 plus 370%. Okay. And this, to produce a fully compressed line, is using 1, 2, 3, 4, then we flip 5, 6, 7, 8, and then this is the 9th one. So we've gone from 12 plus 1 to 8 plus 1, exactly as the maths would suggest. So that's great, and let's count some stuff. So this required 27 stack inserters and 13 smelters. This required just 19 stack inserters and 9 furnaces. So 27 inserters down to 19 inserters. So that is definitely a win, right? For the same amount of output, lots less. Right. What else can we do? Well, JD showed a trick for decreasing UPS, where instead of bringing, let's mock it up to the side. Okay, so we could have a situation like this where we pull off periodically from a belt. The issue here is every time you pull off from the belt, you need to do some calculations to work out where the plates are and are not, well, sorry, in this case the ore, where the ore is or is not on the belt. Every calculation like that requires some UPS. So if you've got lots of it, that's a lot of UPS. The trick is to flip this around. So okay. So if we now had a couple of bits of belt there and there, that leaves us one space where we can fit a stack inserter. Now, as material comes in the bottom, most of it will go through and through. However, a bit of it will get pulled off sideways. All the stuff that gets pulled off sideways is going to saturate this belt, which means this belt is going to tend to be either full or empty. Then the stack inserter will grab a full stack of items, which I think is 12. So then 12 items will be ripped off, but then immediately this will back up, particularly as we're using fast belt. So this belt here is going to tend to either be full or empty, and in both those cases, it's easy for the calculations to happen. So, whereas this line here is a lost cause, right, because we're pulling stuff off it, but the material is going to tend to feed to the right all in one go, because there'll suddenly be a gap. So that's going to tend to mean that this has nice big gaps in it. Again, meaning that we have fewer blocks of material, so fewer computations. So what we have here is essentially this. So you see this thing is full, some stuff gets grabbed off, it remains full, right? It packs up immediately. We could probably improve this even further by doing a priority. So that's fine. And that hopefully improves our UPS. We're still outputting onto this underground here. So we can do the same thing for the other side. So you would be bringing in your line that you're keeping full over here. You would be loading onto that belt there. And because we're neat and tidy, I want to have an input priority and an output filter. Right, so I really want this line to get compressed, which means I want to be pushing material into it all the time. So I prioritize emptying these sides. Okay, so how do we squeeze that in? Now this was fairly straightforward to squeeze in. It's got one overhang below, so I just needed to move these two beacons down one. However, to fit, let's make a little blueprint of it so you can see. To fit that, we need an overhang above where this beacon is. And that was a bit of a head scratcher, except then I realized that you could actually move this beacon up one and there's room for it. So by having the beacons offset rather than in a straight line, we end up with this build. So this still has 12 beacons affecting it. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Still a 12 beacon build. But we have managed to improve it now so that these are always working on a little spur belt. So this spur belt is going to tend to be either full or empty, depending upon the state of the arm, which means all these bits are not being computed, and hopefully the backbone then is having fun. So all good. What can we do to improve this? So this is where we start needing to turn on debugging tools. So if we press this, let's go over here because it's easier to see. Right. So the white lines are belt which doesn't need any computation. The blue lines are chunks of belt which are carrying material and which the computer needs to calculate the motion of. And you can see, so this inner belt, which isn't being loaded at all, is white, all the way up to here to the balance, because that whole lane of the belt doesn't need recomputing, it is empty. Then as we're putting material onto the belt, you can see blue bits appearing, because it's having to track that material. Okay. Then if we go up here, you can see there's lots of broken up blue and white. So it's having to compute things about that the whole time. And by the time we get up here, it's really scruffy, right? Loads of bits, loads of chunks of computation. Every chunk of computation needs some compute. So this one that's outputting with stack inserters is slightly better, right? But you can still see there's bits of white traveling up the inner lane here, until we get up near the top where it's solid blue, almost solid blue. So how does this improve? Here is our 12 beacon build, right? And because it is shorter, there's less belt. So there's less space for the discontinuities to sit in. So it's a bit better behaved for UPS. Also, you've got things like this spur here is usually white because usually the material is static because it's backed up. Okay, so this is improved for UPS. You can see the ore line here has blocks of blue and white going all the way up it. It's nowhere near as flickery as these two. Okay, right. Here's our one that has the intakes. So you can see the intake here is white. Then this is essentially always white, then it fills up, white fills up. Right, so let's carry on all the way up. And again, so this is essentially white until it fills up. I think we can probably get rid of that, right? And we can replace that with that. Okay, so that's a marginal improvement. Great. And we could shorten this off by one tile. I mean, we're really chasing the fractions here. And I think we could probably improve this by having a prioritized output so that it's prioritizing filling up the belts. But again, we're chasing very small fractions here. So these are essentially white all the time. Yeah, that's done the job, right? So then what can we do the other side? So this was where we had the output splitting with priority set. I'm going to set priority here as we did over here, just because I think that's neater. Run down. There we go. Okay, so here you can see the output lane this side is white, this side is usually blue, but goes white each time some output is there. This here is blue permanently, pretty much, all the way up to here. So that means there's a single block of computation, and then where this merge happens periodically to calculate the merge, this flashes white. So carry on up. Now this is great. So now we've got a block of white up here that goes all the way up. Then there's some computation that needs to happen, but this inside lane is, there's a lot of white with the occasional blue. The lane on here has these little flecks of white, and what that is we're running 1, 2, 3, 4 of these, flipping over the lane. Remember, we needed 4 for each side plus a fraction, so that's not quite fully compressing the inner lane, hence these little flecks of white traveling up. Right, so these little flecks of white seem insignificant, and we fill them in here, so we've got solid blue, but these little flecks of white are UPS on that right-hand lane, and it's the right-hand lane we're not doing anything with for half the build. So half the build we're paying UPS for something we're not using. In the meantime, these are churning out onto the far side. Then you can see this lane here becomes bluer and bluer and bluer until the final one when it's solid blue from here on. Okay, so it's kind of sad to be paying UPS for that inner lane with these little sparks of white until the very end of the stack. So what would happen if we moved the extra smelter, the balancing smelter, from position 9 to position 5. So if we did 1, 2, 3, 4 outputs to the far side, then instead of this being where we flip to the other, we would have this machine put half its material on the far side, half its material on the near side. Then we would do another 4 items on the far side, having flipped everything around. That's what we have here. Okay, so this has 1, 2, 3, 4 of these. Then this machine has 2 outputs. It is putting out to this spur, and this spur is loading the inner lane. We are also taking the output from the 4 previous machines and side loading them onto the inner lane. Then we're using this splitter to make sure the priority split is going to send all the material it can to the right hand output, which means then it's going to be side loaded to the right hand of this. And because this gets to put things on the lower side of this, it's prioritizing material coming up for the side loading. This is just filling in the gaps. If you look at this, this means that this bit of track here is solid blue, right? Which is awesome, because now we have a single computation block running up all the way to here. So we have managed to turn a bitty lane with lots of flecks of white into a solid blue lane by putting our top up halfway down the stack. So we're now only paying compute for the first half of the stack for that lane. Then this one carries on doing its thing, and you can see things get side loaded, and as you would expect. Okay, so that's great. Every time one of these stack inserters outputs, we've got a flash of white as it recomputes. And it's outputting frequently because it's outputting whenever the stack inserter swings and finds something in the machine, right? And it's outputting 2 or 3 plates at a time. If we look here, yeah, 1, 2, 1, 2, 1, 2, 1, 2, 3, 1, 2, 1, 2, 1, 2, 3, right? Stack inserters can move a lot more than 3 items. I think they can move 12 in a single swing. Okay, so what can we do to improve that? Because if they were moving 12 items in a single swing, they'd be swinging less frequently, and so the belt would either be empty because there was no swing, or it would be filling up or full because you were dropping 12 items onto it. So the thing to do is to set up a timer. So this has an input of t plus 1, an output of t. So if you put in 0, it's going to do 0 plus 1, output 1t, 2t, 3t, 4t, count, count, count. Then we have a decider combinator. What this does is say if t is less than 55, output the input count. So t is 1, 2, 3, 4, 5 up to 54, output the input count. When it hits 55, this condition is not met, so it's not going to output the input count, which is equivalent to outputting a 0. So that's going to reset t back to 0. Then this will have a t of 0, it's going to output a t of 0 plus 1 is 1, go in here. 1 is less than 55, tick, 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 counts up. Then we have another decider combinator, which whenever t is 0, outputs 1 copper plate. And we send that out on the green wire. Then we have this filtering stack inserter, which sets the filter based upon the signal coming in, right? So every 55 ticks, the filter on this will be set to copper plate. Every 55 ticks, it will then grab all the copper plate it can in here, which is about 8 items, 8 or 9 items, depending upon where we are in the cycle. It's then going to drop 8 or 9 items onto this belt. So this belt, you can see, is either blue or white for periods of time, whereas over here, it's constantly flickering. Okay. So we have now cut down the flicker there. Did I? Yeah, I want to be consistent about this. So let's do the priorities on there. Okay, and we'll put the priorities on here as well. Yeah, that's it. Great. And I've unconnected a power pole. There we go, that's better. Okay, so with these stack inserters, with the filtering stack inserters, we're now picking up much more material per swing. Which means that these things are tending to be either white or blue, and the number of white and blue blocks is much lower than here, right? So we're putting in items, what? 1, 2, 3, 4, so maybe 4 times a second. So 4 times a second, we're putting in a discontinuity between blue to white, white to blue. So that's 8 discontinuities a second, which then all have to be computed and merged back. Here, we're only doing a swing about once a second, every 55 ticks, which is just under a second. So the number of white and blue discontinuities, switchovers, is really low, which is great because that's what we want, right? So let's travel up, and this is where we had to do something a bit different. So this is on the timer. So once every 55, this swings, puts whatever it can find in here onto the outside of the belt. This is the same inner belt contraption we had before, except we're using a standard stack inserter without any wires. This is to make sure that this is always fully compressed, which means that our inside lane is always fully compressed. So this is swinging as fast as possible, which means this is always full. This is taking all the excess and dumping it out. So that means our inside lane is now always blue, as before. Our outside lane now has far fewer holes in it, and you can see it's actually doing long periods of flickering to pure white, which means that there's no computation going on. Okay, and it's only at the very end, when we get our final bit of material in, that we are going to permanent blue. So if you look at this, it's flickering all the time, lots and lots of little blocks. This is very few blocks, and they are very stably either white or blue. So basically this build is going to be the one that's more optimal for UPS, unless I have completely misunderstood how to view this. Okay, just in case, where are we? Were we on basic or detailed? Yeah. So the things you need to check are show active state, show wake up lists, show transport lanes, show transport line gaps. So if you do those, you get these extra displays. The other thing this gives you is, so there's a red circle on this. It shows that that is not currently doing anything, no computation. And this inserted, you can see it's got a blue circle on it, so it's not doing anything when it's got the blue circle. So you want to see lots of red circle. You want to see lots of red circles, that's ideal. Anyway, that's it. So we've managed to go step by step from a fairly hungry, inefficient build to one that should be quite UPS friendly without any loss of throughput. All right, thanks very much. Bye.